So can I start? Should we wait for other participants, or you know that?
No, I don't know. But you can explain your general. No, maybe you can just talk about what is the goal and just slowly start.
Okay.
And then if somebody comes, then comes. If not, then.
Okay, perfect. So maybe we'll first, well, tell something about myself. So I'm Floris, that's my first name. I'm doing a PhD here in Ghent. My two supervisors are Gert de Koolman and Jasper de Bok. I'm doing my PhD in a research group. The name is FLIP. That's over here, FLIP. And it stands for the Foundations Lab for Imprecise Probabilities. So generally, we're just trying to describe uncertainty without making use of probability. So doing more general things such as probability intervals. 2 years ago, I started working on the intersection of two different fields, namely algorithmic randomness, which you're also very used to, and we try to allow for imprecision, namely for imprecise uncertainty models in algorithmic randomness. The reason why I'm here is because I wrote an email to Alexander Schran and started the correspondence. And he suggested that I, started by, for example, by giving a presentation, which I'm doing now. I had some ideas about what I wanted to tell. Namely, I thought maybe I can talk a bit about the first steps that we've undertaken in allowing for imprecision, some open questions. But then on Wednesday, you sent another email saying, okay, it's nice that we're having you on Monday, and I will ask you the following question, namely, what is the connection between what you're doing and what we're doing?
No, not necessarily. So well, let's see what is happening and what you say.
Well, I try
also, I have a kind of, just for politeness, I ask at least the Russian participants who are not in the middle of the complete disaster to switch on the cameras so our speaker can see are we happy or not or yeah. So if
for politeness we should switch off the cameras maybe.
Okay, but no, I see that everybody is in the middle of disaster because they are afraid of showing this bardak, as they say in Russian, showing them. Okay.
So usually I have one slide in which I present my colleagues. So this is the research group, but some of my colleagues joined, which are Alexander Reigers, my supervisor, Jasper de Bok, Arne de Gat, and even they are not putting on their camera, which is quite strange. So well, I encourage you to do it.
So I am Floris. I'm fully visible, Floris.
Oh yeah, it's true. Sorry. Okay.
Not fully, but visible. Yeah. Okay. Let's start.
So what I try to do is, so on Wednesday I received this question of Alexander, what is the connection? And I try to focus on that because I think that's an important question. What's the connection between our framework and yours? So on Thursday, I started reading your paper that's on Archive that was first published in 2011. Well, I try to read certain parts of it. And so in this presentation, I will try to make a connection. There are still some gaps. So during the presentation, I will just ask your help. Well, definitely of Alexander. And
no, just try to provide your part of you and we can discuss. Don't worry if it's something.
If it doesn't work out. Okay.
Yeah.
So that's actually what I'm trying to, what we will try to do then today, some first steps to explain what we've done and then see if you can make connection between your framework of allowing for imprecision and randomness. Okay, first of all, why allow for imprecision? Classically or historically, in the first notion of randomness, we only consider randomness of an infinite sequence, which is our main mathematical object, infinite sequence of zeros and ones, with respect to a certain probability p. But now we can, for example, also consider two different unfair coins. For example, with a green one with having probability p for having, I think someone is eating, but okay. For example, one green coin that has probability p for having heads, or well, 1, and probability 1 minus p for having 0, and similarly a red coin with probability q for having 1 and 1 minus q for having 0.
And if P and Q are very close, it's strange to distinguish between this or that. That's what you are saying, I guess.
Yeah, but well, I will assume that P and Q are different. And now I will use them to generate a sequence. For example, I can generate a sequence of zeros and ones, and at the odd positions, I will use my green coin, and at the even positions, I will use the red coin. So now I could, well, try to describe the uncertainty that is inherent to this infinite outcome sequence in several ways. First of all, I could adopt a precise way of looking at it, but then we should use non-stationarity. For example, you could use an uncertainty model that at even positions, for example, outputs P, that tells us the probability for next outcome at odd positions equals P. For having one at the odd positions equals P and vice versa for Q. But what we also could do is adopt an imprecise perspective and, for example, stick to our stationarity. And then, for example, you could wonder whether we could describe the uncertainty inherent to this infinite outcome sequence by adopting a probability interval, a closed interval that contains P and Q. For example, if you assume that P is strictly smaller than Q, we consider the closed interval PQ. The question is, of course, if you want to do this in the context of algorithmic randomness, first of all, how to allow for this probability interval, how to allow for the imprecision. Furthermore, we could also ask, okay, if this path is generated by these 2 points, if we can describe this uncertainty by this interval PQ, can it also be described by any interval that contains this interval that just contains P and Q? And furthermore, what's the difference between just sticking to a precise approach? What's the difference between the precise notions of randomness and imprecision over there? So these are just some questions that you can ask, and I will try to solve during this presentation.
But
now
wait a bit. So there are 2 possible questions. So you don't try to distinguish sequence to find out whether a given sequence is obtained by this green or red. What you say that there is some sequence and you want to check whether it can be obtained as a mixture of this green and red coins, maybe even an odd or something like this.
So I'm just considering infinite sequence of zeros and ones that is generated by actually a non-stationary precise model. So I just seen this as an introduction to that.
And there is imprecise, more general model. Okay.
Yeah, there's a more general, and so that what does it mean? First of all, what does it mean for allowing for it, etc. So classically speaking, there are several notions of randomness: Martin-Löf randomness, computable randomness, Schnorr randomness, and so on, and they all have different definitions in several frameworks. We have measure theoretic, complexity theoretic, and martingale theoretic notions. Now, the notion of randomness I will focus on today is one of Martin-Löf randomness, because there's also a notion of randomness that you adopt in your paper. By reading that paper, I also noticed that the things that you're doing are more situated, your notion of randomness or imprecise notion of randomness are more situated in measure theoretic notions, and complexity theoretic, where we adopt a martingale theoretic notion of randomness. So I will first try to introduce what our martingale theoretic notion of randomness, what kind of uncertainty models that we allow for. Then also prepare some slides to quickly capture what you're doing, and then maybe we can find out whether we can marry those 2 notions.
Okay, but let me say that it's not what we are doing. It's just a classical thing invented by Levin long ago. It's this uniform test of randomness and studied by Gatch. And then just we tried to understand this theory and to write a survey with Gatch and others. So
okay.
Anyway, nobody probably read this or remembers this, so you don't may.
Okay, then, well, I will still try to refer to you, but then it's more earlier by Levin, etc. But just to make both points of view clear. Okay. By the way, it's very nice that there's so much interaction of you, Alexander. It's very nice to be able. Well, it feels like I'm talking to someone. Okay, so in order to introduce our martingale theoretic notion of randomness, we'll just start by recapturing what happens in the precise case. So in the precise case, martingale theoretic notion of randomness is defined in terms of a betting game. And we'll start by considering a single bet, what this means, and then extend it to a betting game on infinite sequences. So let's try to get there in the precise case. First of all, we consider a single bet. So we start with considering sample space and a variable x that can take on that is an element of the sample space and can be 0 or 1, but it's uncertain whether it takes on 0 or 1. And now we consider 2 players down here, a forecaster and a skeptic. That's me, that's my hat, and that's the head of my girlfriend. And the game starts by me choosing a probability P that expresses my belief about the variable, namely this P, I think that the variable X takes on the value 1 with a probability p and 0 with probability 1 minus p. Next, skeptic, she's allowed
so
to...
let's explain this more clearly. So there is a sequence which somehow appears independently of both of you and your girlfriend. Just it's somehow no one of you produced it. It's just comes from somewhere, yeah?
Yeah, indeed. But I start with not a sequence, but just a single outcome.
Okay,
and next I will
somebody
extend it
will
to
toss a
infinite
coin.
sequence of outcomes. Yeah.
And you say, okay, I guess it will be 1/3 head. Yeah?
Yeah, for example, that's my guess. Yeah.
Yeah.
And now skeptic says, yeah, okay, well, that's your belief. Well, that can be true or not. I will take you up on a bet. And for that, she will select a gamble. A gamble is just a map from the sample space to the real numbers. So she associates with 1 a real number f1 and with 0 a real number f0. And now she has a certain, well, I believe there's a certain expected outcome, namely the expected outcome of the gamble with respect to my probability model is just equal to p times your gambling 1 plus 1 minus p times your gambling 0. Now, I will not allow my girlfriend or skeptic to select just any gamble. I will only allow her to select those gamble for which I believe she will have a negative or non-positive reward. So I will only allow her if, for example, my probability model is equal to a half. Will only allow her to select those gambles which I believe her reward will be non-positive. And if I then put or visualize these gambles in just a two-dimensional space, then the gambles that I will allow her to take just correspond with this half plane. That is defined by the expectation of her gamble with respect to my probability model, which is here equal to a half, being equal to 0.
So, for example, if you say that you believe that probability is at 2/3, it means that you are ready to take bets according to this 2/3 belief.
Yeah, I allow my girlfriend to take those gambles that I expect to decrease.
Yeah. Of course, according to this probability, they should be shouldn't be unfair, these games. But the rules of the games can be selected in any. No, there is not too much freedom here for this simple example. But in generally, you can select. She can select the rules of the game, just not making it not unfair. According to your distribution.
Yeah. So she can select now any gamble, and then, for example, okay, then someone tosses the coin, it's heads or tails, and then she gets the reward that is associated with it.
Yeah.
Now, this idea, I will extend this to an infinite betting game on sequences. So now we'll move towards multiple bets. So now I do not consider just a single variable, but an infinite sequence of variables. Now, with this infinite sequence corresponds possible infinite outcome sequences of 0s and 1, which an infinite sequence of 0s and 1, I denoted by the small omega, and the set of all such sequences is denoted by this capital omega. I will find the outcome sequence of 0, 1, so I know that's by this situation. Well, I call the situation and denote by a small s, and the set of all those things I denote by this symbol. Furthermore, I need a bit more notation. If this is a certain path omega that we select, then if we index it with 1 to n, we mean by that the situation that consists out of the first n elements of that path. And if I index it by just n, I just consider the nth element. Okay.
It's not very clear why you don't use different letters x and w when they seem to be the same, but okay.
Okay. Okay, so let's move on. Now the betting game starts with again with forecaster. Now he doesn't just select one probability, but he selects many probabilities, namely adopts a forecasting system that associates with every situation in the tree a certain probability model, a certain probability. So, for example, if you're in a situation 1-1, the probability that's output by the forecasting describes his belief whether the outcome will be 1 or 0. Namely, the 1 will occur with probability with this probability, and 0 will occur with probability 1 minus the probability written down there.
So essentially, the forecasting system is just a measure, but you prefer to specify this measure not by just as a kind of probabilities of all cylinders, but as conditional probabilities of getting 1 and 0 after each step, and it's probably better suited for some types of bettings which are not local, which are made step by step. But anyway, by now it's just arbitrary measure.
Indeed, it's just a precise measure. Yeah, it's a measure indeed, that's specified. But well, we call it a forecasting system, and we like to look at the local models instead of the global model, the measure. So as a first step, our forecaster selects a measure or a forecasting system. Next, our skeptic, will take a forecaster up on a bet by selecting a betting strategy. Now she does not just select one bet, but she's associates with every situation a certain gamble. So that's what I wrote down here. She selects a certain betting strategy that associates with every situation a certain gamble. And again, she won't be allowed to just select any gamble. She will only be allowed to select those gambles that are allowed by the forecasting system that forecaster adopted. What does that mean?
This requires more clarification. So the gambling is local somehow. So
Indeed.
after you came to some position, there is some forecasting system which declares some probability, and then the skeptic can make a bet just on the outcome of this specific bit.
Yeah, indeed, so, and again, locally, so for example, well, if we are in here in the situation, then with the situation 1-1 corresponds a certain gamble that she puts on the next outcome being 1 or 0, but she won't be allowed to just take any bet, but only the bet that is allowed locally by the forecasting system in the following way. For every situation, the expectation of the gamble with respect to the probability that forecaster associates with that situation should be non-positive. Okay.
Sorry, so F sub S is just a pair of numbers formally, right?
This
For
thing
each
down
S.
here? Yeah, indeed.
Yeah.
Just a set of gambles that associate with every situation a gamble. Yeah. For next outcome, well, the bets on the next outcome being 0 or 1.
Yeah, but then it's somehow what is strange to me, but maybe you can explain. So why then you should provide this forecasting system from the beginning? If you you can say that in general we have a kind of a martingale. So you provide a measure and the skeptic provides a martingale, which is more or less the gambling system. But it's not can be negative super or sub-martingale or something. But so then you say that somehow you want to split the gambling step by step.
Yeah.
But then why don't you split you say you forecast the next bit, then there is a betting strategy, your adversary provides the betting, and then the bit appears. And this is I think Volodya Vovk and other people always like this sequential, that's how they say. But you somehow partly do this.
You're talking about, I think it's called the frequential notion of randomness. There's a paper about it by you, I think, and Vladimir Vovk. Is that what you're talking about?
No, even before that, Vovk, Schaefer in their book always say that there is a forecaster, there is a skeptic, and there is nature. The nature provides the bits, but in their setting, everything should be sliced by time. And another setting, you don't slice measures, you don't slice martingale, you just consider them as general object. But strangely, you do it somehow partially. That's what is a bit strange for me.
You mean it confuses you that we're giving this forecasting system or this measure beforehand, or?
Yeah. So you somehow you want to do it beforehand, but then you split the game into parts. But no, it's completely okay, but still a bit strange. But okay.
Yeah, it's something I want to think about, but or I want to come up with a definition that more sequential approach. But
okay.
That's future work.
Yeah.
So, okay, we have a forecasting system, we have a betting strategy. Well, this is not yet a betting strategy that will test randomness. There are some more conditions. So, okay, we have forecasting system, betting strategies, or skeptic can select gambles that forecaster expects to decrease. And then I will turn to these martingales that you referred to. So with every betting strategy, we can connect a capital process, which is just a map from the situations to the reals in the following way. For example, if a certain infinite outcome sequence or just a finite one is revealed, for example, 1, 1, 1, 0, then the capital of skeptic will change according to the betting strategy that she adopted. So if this is, for example, your situation, we will assume that she will start with initial unit capital. So we start in this initial situation down here, and according to the betting strategy, her capital will then change in the following way. First of all, we move, well, the next outcome is 1, so her capital is increased with the gamble that she specified in the initial situation that we denote with the square, and then they took on the value 1. Plus, then we are in the situation 1, so a betting strategy specifies a gamble in that situation with the value in 1, and then next we're in the situation 1, 1. We add, well, this gamble as well, and we furthermore add this gamble. So,
so you just make some total accounting. What if you know the strategy, you know the sequence, you then will know how much money the adversary will have.
Yeah, indeed. This is a capital process, so we'll assume that, as I just tried to describe, that she starts with unit capital. Furthermore, her capital process changes according to the betting strategy that she adopted. And we will also impose that her capital process in any situation is non-negative, in the sense that she cannot borrow money, just as is done in, as is done in the classical case. So, and this kind of capital process is what we call test supermartingales for the forecasting system. And all such tests, we collect them in the following sets. In order now to obtain a notion of randomness, the only thing that we're left to do is just impose a certain effectiveness on this betting strategy. So we'll impose some kind of computability restriction. So, well, all of these mathematical objects now allow us to introduce the precise notion of Martin-Löf randomness, as it's well known, namely an infinite sequence of zeros and ones, so a path, is Martin-Löf random for a forecasting system. If no test supermartingale, that is lower semi-computable, is unbounded on omega. So two more things to explain. A test supermartingale, a test being unbounded, means intuitively that skeptics should not be able to become rich without bounds. Mathematically, that translates into the capital of your test supermartingale evaluated along the path. The limit superior of it should not be equal to plus infinity.
Excuse me, just to make it clear. So we do not allow the skeptic doesn't know our prediction of the probability.
No,
right?
Skeptic should know. No, maybe the basic first question is whether you assume that for the distribution of this forecasting system is computable. Because if it's not computable, the question whether the other side has accept to the probability.
No, wait. Do we require that phi is computable?
So in our framework, we do not require that this is computable, although we have some propositions, of course, that only hold for computable forecasts, but we do not require it.
Okay.
But then you should not say Martin-Löf random. Because Martin-Löf random is not really well defined from non-computable things.
Yeah.
But then there are some kind of questions whether it's a bit, you should say something, because the opponent has to find make a bet.
Yeah.
And it somehow is natural then while making a bet
to know
what is allowed and what is not. And if phi is not computable, what does it mean lower semi-computable test?
Yeah. So what we do is actually we don't, if the forecasting system is non-computable, we don't give it as an oracle. So we just say there is some forecasting system. There are some tests, some betting strategies that are compatible with it. And we use this one then to test the randomness of this path with respect to the forecasting system.
Yeah, it's
So-
kind of unfair because
It's a kind of blind test, I think. You call it as
don't,
that.
yeah. You don't tell the what is the prediction and ask to play the game. And if somehow the games the bet are inconsistent in terms of this prediction, then somehow you win unfairly, so to say, because you didn't tell the prediction and ask for making bets. But
It might even be that the forecasting system, uncomputable, is so that there is no lower semi-computable test except the trivial one, the all zero function. Because
all
if
one.
we do not know the forecast, we can't make any bet except zero, right?
Yeah, and in that case, you could say that all paths are random. So it doesn't
Yes.
make a lot of sense to adopt that forecasting system. It's a bit of a false notion of randomness then.
Yeah, okay, but so there is a delicate point. What should be known to the betting party? Okay, but still, let's if you say this definition, let's be definition. It's not Martin of randomness, but for a while it's okay.
Okay.
Yeah.
Well, I will continue using, I guess, the notion Martin of randomness.
Yeah.
Well,
Just for today, we believe that Martin of randomness is this, but okay.
Okay, great. So such a test, such a betting strategy should, well, not allow skeptics to become arbitrarily rich in the sense I just described. And so our test should also be lower semi-computable in the sense you're used to probably, namely the test is lower semi-computable or, there's some recursive rational map from situations across the non-negative integers to the rationals, such that this map is non-decreasing in n, such that at every situation when you take the limit for n going towards infinity, well, that number is equal to the capital in that situation. So that's just the classical
It's a standard approximating from below, but without any convergence guarantees. Yeah.
Okay, so let's now allow for imprecision. Now that we know what the precise definition is, in order to do so, well, what I think is the most easy way to introduce it just by, I just copied my slides, I pasted them again, I put everything in gray, and I just added black new things where things change according to the precise definition. So first of all, I again look at the single bet. So we again have a sample space, a certain variable, it takes on a certain value. But now our forecaster will not adopt a probability, but a probability interval, a closed probability interval, being, well, a closed interval that is a subset of the unit interval, and a set of all such unit intervals we denoted by this object. Now, forecaster does not have an expectation with respect to a probability interval if it is not a singleton, but we consider an upper expectation now. And the upper expectation of the gamble f with respect to this probability interval is equal to the maximum of the linear expectations of the gamble with respect to the probability for all probabilities being in the closed probability interval. Now the question is, which kind of gambles will a forecaster allow skeptic to consider now? And these are the following one. He will, well, adopt a conservative approach, and he will only allow skeptic to adopt those gambles that he expects to decrease with respect to every probability in his probability interval. So that means that he's only allowed to select those gambles that are in the intersection of all half planes that are construed by the precise probabilities that are in that probability interval. In that way, as I denoted there, you have like an intersection of different half planes. So you get a cone of gambles now that is available. So what you immediately see is that when you allow for imprecision, the number of gambles that are available to skeptic decreases with respect to, well, adopting a probability.
Yeah, so let me check whether I understand correctly. So you have some kind of family of distributions. So you, in the first step, you allow any number between some p and some q, and that's okay. And the same is done on the second step, but this interval can depend on the zero head and tail, and can be different for two vertices, of course, as before. But also it cannot depend on the number chosen on the first stage. So kind of your class of allowed measures is somehow restricted. So you restrict only the intervals on each level. You cannot say, for example, that on the second, so we have some p between one half and 1/3, and then we 10 times use the same p.
The same probability interval, you mean, or?
No, we can use the same probability interval. But
Well,
we cannot say that we toss the same coin, but with probability between 1/3 and 1/2.
Yeah. So
that's a kind of special kind of restriction.
Indeed, let's wait for the next slide where I'll move to multiple bets, and then it will immediately be clear what I allow and don't allow.
Okay.
So the gambles that he allows is just corresponds with those gambles for which the upper expectation of the gamble with respect to the probability interval is smaller than or equal to 0, which I also denoted here. So that's now our condition for gambles that are allowed. Let's now continue to the next slides where we consider multiple bets. So I have the same slide. There are just a few things that changed, and there's the following. Now our forecasting system can be imprecise as well. Oh, well, that's a bit odd. So now forecaster starts a betting game by specifying his measure, well, not his measure, but his uncertainty model. And now he associates with every situation a probability interval. And that probability interval can be different for every situation.
Yeah, so it's just before, instead of one probability for a given prefix of the game, you select some interval. Yeah.
For every situation, yeah. So given that a certain sequence has occurred, my interval then describes my belief about the next outcome being one possible. Yeah. Okay, and then well, a certain thing that I will maybe use later on, we can associate with any such forecasting system two different what we call a process, namely two different maps from the situations to the real numbers. Namely, we can split this thing in two parts. One thing that associates with every situation, just the upper bound of every probability interval is associated with every sequence, and the minimum, vice versa. And the set of all such forecasting systems, we know that with this symbol over here. Now again, now skeptic is allowed to take a betting strategy. She will not be allowed to take just any betting strategy, but again, locally, forecaster should believe that her gamble is non-positive. And then you just perform the same steps. So now we have forecasting systems towards probability intervals. She adopts a betting strategy, which he expects to decrease. We can correspond capital process with it in the same, exactly in the same way. We start with unit capital. Her betting strategy expresses how her capital changes. She is not allowed to borrow, and we impose some computability restriction over there. So the only thing that actually changes with what I described before is that we now allow for probability intervals, and that the set of gambles that she is allowed to select is specified by this condition over here. And this way we can obtain a different notion of Martin-Linear randomness that now allows for imprecise forecasting systems. Namely, now a path in a different sequence of zeros and ones is Martin-Linear random for a forecasting system, which we now allow to be imprecise in every situation. If again, no lower semi-computable test supermartingale is unbounded on omega. And that's it regarding our imprecise notion of Martin-Linear randomness.
Yeah, it's a bit, there are some subtle points which I think should be mentioned here now. So you require that lower semi-computable is the super martingale.
Yeah.
Not the betting.
Yeah, indeed.
Which is a bit strange because the super martingale are just the combination of the betting and your
well, I try to introduce this for those folks that are not really used to betting strategies. I try to introduce it starting from the gambles, because I thought maybe it would give a bit more intuition. But indeed, you could indeed impose, for example, that the gambles are lower semi-computable, which are here now additive gambles. You could also consider multiplicative gambles and build a capital process based on that and impose lower semi-computability on them. But well, here we opt to do just as in the as is done in the precise case in Martin-Löf randomness, to impose lower semi-computability on the test supermartingales. We could do that as well, but then probably we'll get other notions of randomness.
Okay, let's do like this.
For example, we actually
Maybe
have,
just can I interrupt for one of the reasons is because I totally agree it's weird to do it on the capital process itself. One of the reasons is otherwise you don't get equivalence with the normal definition of Martin-Löf.
No, but since the normal definition is only for computable measures, then we still have the equivalence. So this is.
Do you? I don't think this is fixed by making phi computable. I'm not so sure that's the case.
and if it is the case, we would really want to know what the proof is behind it or the idea.
To have it lower semi-computable bets.
So from lower semi-computable bets, it follows that the capital process is lower semi-computable, but the other way around.
So we want to have this. So the bets are difference between two lower semi-computable numbers. Yeah.
Yeah, indeed. Yeah.
But
Exactly.
for Martin-Löf randomness, we may consider lower semi-computable martingales.
Martingales,
Okay.
yeah, but I think the thing where it
then-
goes
then
wrong
the bet
is because the initial situation is not known. You need to have if you know what your initial situation is, then you can use your initial situation, and then from that, well, if you have a martingale, you know how things actually, if you know what the initial situation is, then the whole thing would be computable. Because if you have the martingale condition and you just
No, of course we
below,
should consider martingales, but with lower semi-computable capital at the beginning, not one.
yeah,
To
but
get equivalent definition of Martin-Löf randomness, but
yeah, so it's just equal to 1. So it's and because you don't know the exact initial capital, that's why we believe or think or thought until now that it's not possible.
yeah.
That is different. For example, an idea that originates from a paper that you wrote, Alexander. Maybe you can help me. I forgot the title, but it was about the splitting of martingales in the notion for lower semi-computable ones. It's a paper I recently read. It was a result by Mechanico. I don't know if I pronounced it correctly. So it was an idea that the lower semi-computable martingale, submartingale, I don't remember that well, cannot be splitted in bets on even and odd positions.
Yeah. It's just.
Yeah, and you can use that for the following. We also define the notion of Martin-Löf randomness, which we call weak Martin-Löf randomness. It's a bit different from this one in the following sense. The betting strategies that we are considering, the gambles, we don't consider an additive betting strategy, but a multiplicative betting strategy. And we impose on the multiplicative betting strategy that it is lower semi-computable. And if you do that, we can use the result in your paper to show that you end up with a different notion of randomness with respect to Martin-Löf randomness. So, for example, by putting or imposing the lower semi-computability on the multiplicative bets.
Okay, no, okay, no. So no, I just it should be known for Martin-Löf randomness standard, for example, even with uniform measure, whether we can use kind of restriction on bets, not on the martingale. But I don't. Maybe somebody knows. Bruno, maybe you remember what kind of restrictions we can have on bets to get equivalent definition of Martin-Löf randomness for.
I only know what Floris just said. I think you can diagonalize it. It should.
So you
Should
think
be
that
negative,
if
yeah.
we get not if it's asking for bets, it's not what not will be not equivalent. Okay, let's go on and see.
Okay, so what time is it? Okay. So well, now we have an imprecise notion that coincides with the notion of Martin-Randomness in the precise case for then computable forecasting systems. Furthermore, what we also did is we did not only render.
Sorry to interrupt. So some basic questions. The forecasting system that assigns 0-1 interval makes every sequence random.
Yeah,
is it right?
Indeed, that's yeah. Well
so
spotted.
even the all zeros and the all one sequence.
Because you cannot make any reasonable bet, because your bet should be stable under all possible. You are not allowed to win against 0 and against 1. So there is not much chances to become rich.
The gambles that correspond to with the unit interval are those gambles that are non-positive. So actually, skeptic cannot acquire money because our gambles don't allow her to acquire money. So indeed.
So if P is 1/4 and Q is 3/4, then the sequence who are not random, they must have like much more than 3/4 of ones, and then the limit frequency.
If they alternate 0 and 1s regularly, they will be not random, even if they are. It's not, of course, not. Not only frequencies is important, but.
But I say all sequences for which a limit frequency exists and this limit frequency equals 0.9 will be non-random in this gambling system. Yeah, just to check the basic line. Okay.
Yeah, well, we also have, the frequent, you're mentioning frequencies, so that's more like church randomness or church stochasticity, because in some groups I need to be careful, apparently. It's not considered to be randomness notion. And we also have, an imprecise notion of church stochasticity, of church randomness, as we like to call it. Well, let's see if you agree on that or not.
He just says in one direction. If the frequency tends to 90%, then the sequence cannot be Martin-Lev random just for this reason.
Yeah, indeed. If the probability interval is smaller, so indeed for this, Well, I will immediately move towards frequencies. First of all, I'll just quickly mention, and will not try to go into too much detail on this, that there are also other notions of randomness, precise notion of randomness, such as computable randomness and Schnorr randomness. And we also came up with, definitions, for example, for computable randomness and even church randomness, but I will not focus on them because it will be too mathematically heavy. I will just mention, which I find interesting now because Bruno mentioned it, that we also have some kind of frequentist notion of randomness that we introduce. And this notion, we look at relative frequencies along our path that we consider and along recursively selectable infinite subsequences. So, just as in the classical approach, in order to select an infinite subsequence, we consider a selection function, which is a map from the situation towards 0 or 1, and just selects an infinite subsequences in the classical way. For example, if we have a certain path omega, like this, etc. If the selection function in the initial situation is 1, then we select 1. Otherwise not. If the selection function in the situation 0 is 1, then we select the next entry 1, otherwise not, etc. and so on. And now we can introduce a more precise notion of church randomness. Namely, we consider a path omega to be church random for now, or kind of forecasting systems, or kind of imprecise uncertainty models. If for every selection process that is implementable, that is recursive, that can be computed by a Turing machine, that selects an infinite subsequence of the path that you consider, that's what this thing says, it holds that the frequency satisfies these conditions. And these conditions are quite intricate, so we'll just move towards a more simple uncertainty model to give you intuition. Namely, if we consider a stationary forecasting system, namely a forecasting system that associates with every situation a probability interval. So we look at a fixed probability interval. Then a path is church random with respect to that interval. If for every selection process that is implementable, that is recursive, that selects an infinite subsequence of this path, it holds that the relative frequencies of ones along the path that is selected by the selection function resides, well, in the limit in between the bounds specified by this Bayer probability interval. So we don't, well, we don't require that that limit exists, as Bruno well said. And what we proved is, for example, for every probability interval, if a sequence is Martin-Löf random for it, then it's also church random with respect to that probability interval. But so then these frequentist conditions apply.
The original church definition assumes that there is some fixed probability of one at every step, but indeed, also you can do it for every distribution. Just you need to subtract not the constant p when we compare the frequency, not with the Pn just, but you just count the expectations with predictions on every step, and then if you have an interval, then you can just consider kind of worst case, something like this.
So you're speaking about Kolmogorov-Loveland randomness?
Not Loveland, because it's monotone selection rules.
Okay.
Okay. So we have also.
Just sorry, I have to just continue. I'll come back.
Okay. Okay. So that's what it's about. Our notion. I will just now just introducing some properties that hold in our framework, which I think are interesting or intuitive. So just to get to give you a familiar feeling. One of these properties is one, as Bruno mentioned, namely that every path is Martin-Löf random with respect to the unit interval, for example. So some simple properties. In order to introduce these properties, I introduced another mathematical object. So for any notion of randomness that you can consider, the notion of randomness being Martin-Löf randomness, Computable, Schnorr, or church randomness, and any path over here, we consider the following sets, which consists out of all probability intervals for which your path omega is random. Now they will allow me to mathematically introduce you some properties which I will just explain in a graphical, intuitive way. First of all, we have some kind of monotonicity property that is given here, but I will just explain by making use of the graph down here. Namely, if you consider a certain path and a certain notion of randomness, being it our precise notion of Martin-Löf, Computable, Schnorr, of church randomness, it holds that if that path is random with respect to this interval, it's also always random with respect to any probability interval that contains the original one. So with respect to any probability interval that is more imprecise.
Floris, wait a little bit, just a second. You think you have defined these notions not only for church randomness? I mean, what means that omega is R random for I? I think you have defined it only when R is church, right?
No, there is also Martin-Löf, which is not Martin-Löf, but still.
but what's the definition? Can you repeat?
Kind of lower semi-computable martingales should not win on these sequences.
But what means for I, capital I?
I think the forecasting strategy that always says I.
Indeed. So a fixed probability interval I. So forecasting system phi, but we just write I because we're just associating with every situation a fixed probability interval.
So phi is constant.
Yeah, indeed. Yeah.
Okay.
Yeah, thanks you for clarifying that. So I just quickly said, so we have our notion of Martin-Löf randomness, church randomness, and we also have an imprecise version of Computable and Schnorr randomness, which I will now not introduce. They are just very familiar to the precise case. I will take too much time, I think. So first property was this monotonicity property. So if a path is random in one of the four senses with respect to a certain probability interval, it's always random with respect to any probability interval that is more imprecise. It's very easy to see because if you look at the gambles that are available to skeptic, the more imprecise your probability interval, the smaller the set of available gambles. Now we also have some other property that Bruno mentioned, namely we also know that every path will be random with respect to the unit interval. And the reason why I'm introducing these properties is because of the structure now, it's very natural to ask whether for every path there is a smallest probability interval, the smallest stationary imprecise description of its randomness. Namely, is there for every path the smallest probability interval for which it is random? And that's the question Gert de Koolman and Jasper de Bok, my two supervisors, asked themselves from the beginning in 2017 when they first published their results. And we were able to answer that question positive in some sense. So first of all, oh, no one is answering. First of all, for the notion of church randomness, well, I've wrote it down too technical here, but for the notion of church randomness, we're able to prove that there's always a smallest probability interval for every path for which it is random. And that's very easy to see because for every path, well, the frequencies do some things along this path itself, along all subpaths. And there's always a smallest interval that bounds these frequencies.
So you consider the interval not depending just one interval for the entire process, yeah?
Can you repeat that, Alexander? I didn't get your question.
So you consider just the same interval for all the steps, yeah?
Yeah, indeed.
Yeah,
a stationary approach. Yeah, focus on a stationary approach right now. Yeah. So what does that say? For example, if we have a path and its smallest probability interval is, for example, 1/3, 2/3, then we know that's also random with respect to, of course, unit interval, but also with respect to any probability interval that contains the smallest interval. But for no intervals for which one of the two endpoints lies strictly in this given interval.
So what you do is just consider all legally selected subsequences and take the frequency lim infinite and lim sub and say where they are be. What are the possible upper and lower bound for them? Yeah.
For the notion of church randomness is very intuitively to see that such a smallest happens, and that's also why I'm introducing it as the first one for which this probability holds. So let me just repeat what we just said. And so for every path, there is some smallest probability interval that specifies actually all other probability intervals for which the path is random. Now, a kind of similar property also holds for other notions of randomness. Namely, if you look at the computable randomness and church randomness, and it also holds that for every path, there is not the smallest, but an almost smallest probability interval for which this property holds. What does this now mean? Imagine that we have a certain path, and now its almost smallest probability interval is equal to 1/3, 2/3. Then we know that this path is also computably or Schnorr random with respect to any other probability interval that strictly contains this original interval. It's also not completely or Schnorr random with respect to any probability interval for which one of both endpoints lies within the interior of your original interval. But something that we cannot say is we're not sure whether whether the path itself is random for the smallest interval itself. So we have some almost smallest probability interval right here. Okay, and for the case of Martin-Löf randomness, it's actually still an open question whether there exists such a smallest probability interval or an almost smallest probability interval for which a similar property holds. So this means that in some sense, if we look at a certain path, there's also always a most precise or less imprecise stationary model that describes its randomness.
So you say the problem is that you have two intervals for which it can be random, but the intersection is not.
Well,
that's the problem, or
the problem for Martin-Löf randomness, or
for Martin-Löf randomness, you say that there is some open question.
Oh, so, yeah, it's indeed a finite intersection property that we would like to prove. Indeed, that's the open question. Indeed, given that the path is random for a certain probability interval I1 and for another probability interval I2, then the question is whether it's also Martin-Löf random for its intersection. Indeed, and that's the open problem that we were not yet able to solve.
Mm-hmm.
That's indeed the open question. And it has something to do, well, the lower semi-computability is a pain in the ass until now. Whereas the computability for notions of computable and Schnorr randomness well, allows us to prove this property. Yeah. By the way, actually, we have a partial answer to this open question. Namely, how did it go again? Let me recapture. Yeah. If if you're considering Martin-Löf randomness in your sense, namely a path is Martin-Löf random with respect to a computable precise forecasting system, for those paths, we were able to prove that there is always an almost smallest probability interval. So if you want to adopt a stationary description, then there's always a smallest probability interval. But that's a partial answer because well, then we only consider paths that are Martin-Löf random in the classical sense.
But I'm confused. Your intervals are constant here, so they are computable if the endpoints are computable.
Well, we don't require the interval, the almost smallest probability interval to be computable. Yeah.
Oh, but say it again. What is the so who is random in Martin-Löf sense? Say it again.
Okay, I just want to say that we have a partial answer to this question.
Yeah, what is the partial answer?
There's a partial answer goes as follows. So, according to the classical definition of randomness, you
with
define,
respect to which measure?
Well, with respect to computable for precise forecasting systems.
Yeah.
So, real Martin-Löf random, according to your point of view, for a path that is Martin-Löf random for a computable precise forecasting system, it holds that there is always an almost smallest probability interval for which it is random. So we know that this property of almost smallest probability interval holds in that situation.
Ah, so you have a sequence, you have a true measure, and then when you consider a random path, Martin-Löf random path with a computable measure, and then you forget about this true computable measure and just want to find this one interval for all steps.
For one path, the one path that you consider.
Yeah, and for this one path, you want to find an interval.
Yeah, and that one exists. Yeah,
and this one exists. And does it depend on the random sequence or not?
Yeah, it depends on the sequence. Yeah.
So can you just for better intuition, it seems that all the random sequence should be the same somehow. Why it's different from one and another?
Okay, well, it is because this measure, well, I look at it from point of view of forecasting systems. Okay.
The smallest, depending on the first bit, it can go in different.
Okay. Yeah. So actually, I can just quickly write down the definition of the smallest interval. I think it goes as follows. I need to write. So you have a certain forecasting system that associates with every situation a certain precise number, a probability. Then we have a certain path that is Martin-Löf random for this forecasting system. Then its smallest probability interval. So the smallest probability interval
is just between inf and lim sup of frequency of predictions along the path. Yeah.
Yeah, it's the lim inf of indeed of, I think it was like that, and then the lim sup. With things going towards infinity, of course. Yeah, so we have a partial answer to that, but we did not obtain there in the direct way. We were able to complete that from other results. So feel free to contribute to that. Okay, I guess.
Floris,
yeah.
Could I just intervene with respect to this question of that it's not close with respect to intersection? If you're random for two intervals, then are you also random for the intersection? So the point of the reason this is an open question, it's not. It all comes down to whether the process, the capital process itself, is lower semi-computable, or whether the differences are lower semi-computable. This stuff we were discussing like half an hour ago. If you would use the definition that the local bets are lower semi-computable, then this property holds. So if you change the definition in this way, if you just require that the local bets are lower semi-computable rather than their sum, basically their running sum, then you do have this intersection property, and then it's all fine.
But for multiplicative betting games, you mean not for additive?
Yeah, but also for additive, I guess, or not? Is it only for multiplicative?
We also only have it for weak Martin-Löf randomness, which is defined in terms of multiplicative
for the positive games. Due to non-negativity. Yeah. Okay. Fair enough. So just wanted to kind of add that the issue is there. It's again revolves around this this subtlety, so to speak, where so if you use the kind of more natural version, actually you do get this property, but then you lose the equivalence with normal
things. Okay.
With normal Martin-Löf.
Yeah. Okay. So now I thought it was maybe a good idea to move back to one of the more initial slides, namely how to allow for precision. Well, the questions we posed. So I hope now you have some idea about how we allow for precision. So we tried to describe this. I also tried to explain well, the idea of a smallest, if you adopt a stationary description, of having a smallest probability interval that describes, well, the uncertainty of the infinite sequence. And there was one more question that I raised, which I find very interesting, and this, that what's the difference between being random with respect to precise or imprecise uncertainty models? And I just, well, give you a result that was proven in a collaboration, well, was proven by Gert and Jasper in a collaboration with Vladimir Vovk. Namely, they were able to prove, well, and the statement of the theorem actually more is given here. They have proven that for every probability interval that is not a singleton, so a real probability interval, there's always a path that is, for example, Martin-Löf random for it, but that is not Martin-Löf random for any computable, precise forecasting system. And that's why we, well, claim that randomness is inherently imprecise. It cannot be explained away. Namely, if you want to, well, have a precise description of, well, if you want to consider, if you consider path as Martin-Löf random with respect to the probability interval, well, you know that there are, sorry, I'm a bit babbling. So you know there are paths that are, for example, Martin-Löf random for this probability interval, but not with respect to any computable precise forecasting system. So if you would insist on precision, then, well, it could very well be, well, then you need to adopt non-computable precise forecasting systems. Yeah. So if you introduce imprecision, it also allows you to describe paths that are random with respect to non-computable precise forecasting systems. But you can describe their randomness in a computable way.
But if you allow non-computable measures, then do you have some kind of equivalence result like this?
Well, this is one of my most recent results that I found this weekend. So this weekend I was thinking about the connection between your framework and ours. And I think, well, a couple of months ago, I wrote a paper together with Gert and Jasper, where, well, my question was, okay, what does it really mean to allow for imprecision? And we came up with the following result for the notions of Martin-Löf, computable, and Schnorr randomness. With every probability interval that you consider, there corresponds a set of paths that are Martin-Löf random or computable Schnorr random with respect to this probability interval. And what we essentially proved is that there is at least one precise with a non-stationary uncertainty model. It has the exact same paths for which that are Martin-Löf random with respect to that model. But that model is non-computable. So if you allow for non-computable forecasting systems.
No, I don't understand. So imagine we have some kind of, so we have a class of measures when the probabilities, conditional probabilities are inside this interval.
Yeah. And
then we consider randomness with respect to this probability interval. And somehow informally, it should be some theorem like the sequence path is random with respect to this interval, if and only if there is a measure where conditional probabilities are in this interval, and this path is random with respect to this measure. So kind of imprecise randomness is just the union of all precise randomness for all hypotheses which are inside this your white hypothesis.
Yeah, well, I found an even stronger result actually. For a probability interval, I proved that there is one precise non-stationary forecasting system, such that all paths that are Martin-Löf random with respect to the probability interval, or Martin-Löf random with respect to this single precise non-stationary forecasting system. I
don't understand. So imagine we have just our interval is, I don't know, between 1/3 and 2/3.
Yeah. So
we
let me
somehow,
write it down.
our hypothesis is that all conditional probabilities are between this 1/3 and 2/3. This kind of Santa Vazirani sources.
Yeah.
And then you can say you have some notion of randomness, and so you say that there is one specific measure that corresponds to this case.
Yeah. So for example, consider the closed probability interval 1/3, 2/3. So with it corresponds, for example, a set of paths that are Martin-Löf random with respect to this interval. Yeah.
Yeah.
Okay. What we proved is the following. Now consider a non-stationary model.
Yeah.
So you have certain discrete time steps. On the vertical axis, well, you have some real numbers. And so so here is 2/3, here is 1/3. And this, well, we will now build a precise non-stationary uncertainty model so that, well, takes on the values 1/3, 2/3, maybe, well, next again, 2/3, 1/3, 1/3, 2/3. And we'll do this in a very erratic way. Actually, we use a special path to consider such a model. So we have a precise non-stationary model that switches between 1/3 and 2/3 in a very erratic way. We proved that there is such a model, such that the paths that are random with respect to this non-stationary precise models, the set of paths, coincides with the paths that are random for a stationary model.
But so somehow you say that you can just suggest one sequence of probabilities which alternates between 1/3 and 2/3 in such a way that everything which can be believed to be random with the intermediate probabilities is random according to this specific sequence of 1/3 and 2/3.
Yeah, that's a result that we obtained, by adopting this notion of randomness. And actually, it is even stronger because this weekend I was working on what I wanted to present here, and I was a bit inspired by results in there. Not by the proofs, because I did not have time to read the proofs. I was thinking, does a similar result hold for arbitrary forecasting systems, not for stationary one, but forecasting system that's associated with every situation a certain probability interval? Now, we still need to check the proof because I had an idea, and this morning just said to Jasper, I think I found an even more general result. But if it holds, then we prove the same thing. Given a certain imprecise forecasting system, so that can be imprecise and, well, different things happening in all situations, then there is a precise one that is contained into that imprecise one, such that the paths that are Martin-Löf random for that imprecise one coincide with the paths that are Martin-Löf random for that precise one that lies, well, in between the original forecasting system. So I think what I just, tried to explain also holds more general, even more for all forecasting systems.
But in your opinion, this is good news or bad news? This result.
Well, I don't know yet. I think it depends on your opinion about whether you think it's important to impose computability on the forecasting systems or not. But by the result of Vladimir Vovk, Jasper, and Gert, we know that there are paths that are random with respect to probability interval, but not with respect to any precise computable one. So if you think computability is important, then, well, that's the importance of allowing for precision. If you, have the opinion that things can be non-computable and then move even more connection with the real world, what we're doing here, then it seems that imprecision is not needed.
Okay, but somehow it's all very strange. But let's. I don't understand. So let's consider your proposition, which you say here about computable precise forecasting system. Let's take an interval. I don't know, 1/3 and 2/3.
Yeah.
And let's take a sequence which has a limiting frequency somewhere between 1/3 and 2/3.
Yeah.
and this limiting frequency, I don't know, is not arithmetical, or just a very high, non-computable in a very strong sense. But if you find computable forecasting system, I guess that all the sequences have limit. If they have limit probabilities, this limit probability should be somehow definable, not?
I'm completely following with the picture you're describing.
Okay, no, just your picture of the proposition. There is a kind of stupid way to prove this result, to attempt to prove this result. And what I want to ask you, why this way is stupid? If it, I guess it is, but why it is stupid? So this way is like this. Take the interval.
Yeah.
R bottom, R top. And take some a real number, which is between R bottom and R top, and is not definable in any reasonable sense, because there are only countably many definable things. There should be something which is not definable in very strong sense.
Yeah.
And it seems that this path, and take a random path according to this to this probability.
Yeah.
It seems that with probability 1, it will be random for your eye.
Yeah.
But also it seems that if something is random for computable precise forecasting system and has a limit, it somehow should happen only if the limit frequency is definable in some sense, no? So just why I'm saying that maybe the reason why it happens, because there are just sequences which are random which are which are random with respect to some very non-computable probability.
Okay,
And this will prevent them from having a compute precise forecasting system.
Yeah. Okay, now I get what you're saying. Okay. Now, the theorem that Wolf, Gert, and Jasper proved is actually even a bit, well, it's more general than what I just told you. I introduced like this because I thought it was the most easy way to introduce, but it's more general. What it actually tells is there is, for every probability interval, there is a path that is, for example, Martin-Löf-random for it, but not with respect to any computable forecasting system that is precise, but we also allow for more. For any computable forecasting system, whose imprecision is smaller than the original probability interval that we're considering. So maybe I should write this down. So you have a certain probability interval, PQ. Then we can prove that there is a path that is Martin-Löf-random for this interval, but not Martin-Löf-random with respect to any computable forecasting system phi. So a map from situations and can also take on intervals, such that its imprecision is not larger than the original interval, with which we mean that, if I'm not mistaken, that at every situation, okay. At every situation, so the probability interval that corresponds with the situation, so its length, so the max of your interval that is specified by a forecasting system in this situation minus the minimum should be smaller than Q minus P. I think that is what a theorem tells. And now, for example, if you adopt, for example, a stationary probability interval 1/3, 2/3, you could say, okay, maybe there are some probabilities in there which are non-computable, but then we can just put rational bounds.
That's of course, but still the question is: imagine we have a sequence which is random with respect to computable precise forecasting system, and it has some limit frequency. Does it imply that limit frequency is somehow definable? Or not?
That these numbers that you obtain, that they are computable or lower sum computable.
No. So we take a measure P, some computable measure P,
yeah,
and we have a random sequences, random sequence and take the limit frequency, assuming it exists. Can we be sure that it's not maybe not computable, but 0' computable or 0,2' computable or whatever? So it cannot be just arbitrary.
Well, I haven't thought about that, so I won't be able to give, give an answer. Maybe.
Yeah.
I guess it depends whether the forecasts will converge. If the precise forecasts of that measure will converge, then okay, that number will equal the frequency. But if the forecasts themselves keep on kind of like going up and down, they never stabilize themselves, then I don't think there's any kind of constraint on the frequency of the path.
But the question is, for every, if you have a computable measure and take different frequency limit frequencies for a random path, how many of them you can have? Can you have a continuum of possible limit frequencies? It's not easy to see how
maybe like you can ask more generally if you have a computable measure and you have like limit of a random sequence with respect to this measure, whether this limit is somehow
cannot be arbitrary real somehow,
or there are rules which cannot be limit of a random sequence with respect to some computable measure or with respect to computable forecasting system.
Okay, there is a Russian proverb which says that I don't know, Bruno probably can even understand it in Russian. So один дурак может задать столько вопросов, что 100 умных не ответит. One fool can ask more questions than 100 wizards can answer. So let's continue.
Okay, fine. Well, that was a bit it for our notion of friendliness in terms of this martingale theoretic framework. Now, I told you in the beginning that I was looking for trying to make connection with what you were doing, and what I read in that paper is that it's more developed in a measure theoretic framework. So if there's still time, I don't know how long this.
Yeah. We have at least 10 minutes. Yes, 11. Yeah.
Well, we won't be able to get there, but that's fine. Now, we also recently, and that's work in progress, we're writing an article about that. We also, we started thinking about coming up with notions of randomness in this measure theoretic framework. We found out that there's some equivalence relation between our notion of randomness for our forecasting systems, that kind of uncertainty models, with respect to martingales and measure theoretic tests. I thought maybe it would be nice to say a few things about that, because according to my gut feeling, that will help to find connection between what we are doing and what you are doing, what other people have been doing. So I will proceed as I did previously. I will just start by introducing things in the precise case, and then just copy again the slides into gray and just change the things that in black. That just need to be changed for our context. So, first of all, if everyone is acquainted with measure theoretic randomness, I can just immediately switch to our definition. That's something we could do as well. But if not, I can just repeat some things that I found in your paper that I'm using now to introduce it. Let me just do it.
Well, we need to understand your notation, so you need to go through the slides anyway.
Okay. Perfect. So first of all, introduce some new mathematical objects. We look at, first define or correspond to cylinder set with every situation. So you write like this. So the cylinder set of any situation S is equal to the set of all paths that are extended or that extend the situation. That's the first thing. And then for any...
so you define the notion of open set in a contour space as a union of intervals. Okay. That's clear, and you can consider maximal intervals. Then they are prefix-free set in a tree.
Yeah, so prefix-free sets, and we just do the same thing. Okay. Next, if you have a certain precise forecasting system, we can define a probability of a certain event to occur. It's just equal to the sum of the probabilities of the situations, with the situation being elements of the set of situations. And the probability of the situations is just defined in a classical way. For example, if you look at situation 1, 0, then its probability is just, well, probability of having 1. And here, well, you just multiply with what your forecasting system tells you, namely phi, your forecasting system evaluated in the initial situation. And then you move towards 0, multiplied by 1 minus the probability that is outputted by your forecasting system.
So if you have a forecasting system, you have a measure, and then you may consider the measure of any open set or even any Borel set or whatever. Okay.
Yeah, indeed. But I like to write it down like this because it's very simple and it's actually the only thing that we need. We don't move. Okay. So then next we can define what the Martin-Löf test is. So let's again restrict ourselves to computable measures. So it's just an infinite sequence of sets of situations, UI. There are some conditions on this UI. First of all, it's prefix free. Furthermore, the probability with respect to the precise computable forecasting system for every event that is associated with the set of situations U indexed by k, that probability should be bound above by 2 to the minus k. And there's one more condition that we impose, namely that the sets should be recursively enumerable in a uniform way. So just repeating what is done in the precise case, so the standard conditions. Now, Martin-Löf test then allows you to consider an effective null set. Null set is just the intersection of the events that corresponds with each u indexed by k. And then a path omega is considered to be Martin-Löf test random for a certain forecasting, precise, computable forecasting system if there is no Martin-Löf test such that omega is an element of the corresponding effective null set. So that's what's done in the precise case. Now let's again allow for imprecision. So now we will allow for forecasting systems that can be, well, it can be non-computable and imprecise. Okay. So, oh yeah, this is what you have been doing, but I will, we'll skip it. I will just first move towards what we have been doing. So in the imprecise case, we're allowing for forecasting systems that can associate probability intervals with the situation. And now we again consider actually the same kind of tests, Martin-Löf tests, which are again prefix free, recursively enumerable in uniform way. But now the first condition changes. What we now do is you have a certain forecasting system that, well, specifies, as I just said, with every situation, the probability interval. And we select now, or we consider every precise forecasting system that is compatible with it. In the sense that you could consider, well, we consider forecasting system of which each real number, well, we consider precise ones here, of which each precise real number that associates with the situation is an element of the interval that is specified by, in that situation, by our original forecasting system.
And these precise strategies don't need to be computable.
No, they don't need to be. You just need all kind of precise forecasting systems that are compatible with it. Then we approach that the probability with respect to every such precise one that's compatible with the precise one, the probability of the the event that corresponds with the set of situations u indexed by k is bound above by 2 to the minus k. Again, this allows us to then consider effective null tests. And now, according to our notion, a path is then Martin-Löf test random for a forecasting system that can be imprecise. If there is no Martin-Löf test, such that omega is an element of the corresponding effective null set. Now, there's one more thing that I need to say. This is how you could, well, there's one more thing I need to say. That is how this measure theoretic notion of randomness connects to our martingale theoretic notion of randomness. And they are equivalent, but not for all forecasting systems. They are equivalent for those forecasting systems that are computable, and that's specified for and that's associated with every situation, not 0 or not 1. So for those forecasting systems that remain away from, that keep away from 0, 1, and which are computable, we're able to prove that our martingale theoretic imprecise notion of randomness coincide with the precise measure theoretic notion of randomness that I just introduced. And I think.
Do you have counterexamples for phi s equal to 0? So phi s not equal to 0 means that 0 is inside the interval at s.
It does not mean that it is not in the interval. It means that the
it cannot be
forecast cannot be precisely. Yeah, it can contain 0, but it cannot be exactly 0 or 1. Yeah.
And so there is a counterexample for this condition.
I don't know.
Computable if it's computable reals, or even if computable rationals, for example, 0 values are also bad.
Can you repeat that now?
Imagine that this probability intervals are just with rational endpoints that are computable. Then also this 0 case is bad, or it's only because of this.
Well, first of all, I actually didn't explain what we mean by computable forecasting system. So we know what a computed real number is. An interval, we consider that to be computable if it's minimum and maximum or both computable. And a forecasting system that associates with every situation the probability interval, we consider that to be computable if there is a certain algorithm that can output for every situation both approximate its maximum and minimum. So in that sense, do we consider forecasting systems to be computable when the endpoints are computable? And
Floris, I think Shen means about, is the issue that the endpoints are not computed, may not be, or is the issue that like where you have which interval is not computable? Is it like these two ways in which it can be non-computable?
Okay,
like just the endpoints themselves, or?
Okay, I just want to ask different, but it's strange that if something has probability 0 and we know exactly what has probability 0, it somehow doesn't change things really. So if we know exactly where the zeros and ones are, I think it could not be so dangerous. But okay, don't worry.
Yeah, that could be the case.
Okay.
Yeah.
Actually, Floris, is this an issue in the precise case too, this result? Does the equivalence break down in the precise case if you have zeros or ones?
That's a good question.
If this was true, we should speak about this. I think there were no problems in the precise case.
No, but it's interesting. So you say that at least for this non-degenerate case, this definition is equivalent just to randomness with respect to a closed class of measures. And so you get some martingale characterization for randomness with respect to closed class of measures.
Yeah.
And which is not quite untrivial. You don't have any martingale characterization for the arbitrary class of closed class of measures.
Indeed. So that's indeed where I think that both of our imprecise theories will connect. We're restricting our attention to this closed class of measure that are defined well with the forecasting system that we use. You're actually allowing in this measure theoretic framework for more general class of compact classes of measures. There are quite unclear things. For example, if you look at you want to find kind of a criterion in terms of complexities or martingales or whatever. For example, for the class of Bernoulli sequences. Yeah. What should you what should you see in the sequence to declare that it's not likely to be a Bernoulli random one? Yeah. And here you have some partial answer for this class of interval predictions, but it's interesting. Yeah. And indeed, I noticed that the kind of Bernoulli randomness that you introduced, it's not compatible with what we're doing with the forecasting. Well, it's a different setting. We require the same. We don't require anything about probability except for being the same on every stage. Indeed, and you require what it is, but do not require this. Do not allow any connection between different steps. But okay. Yeah. Okay, that's then the point. Well, I did not introduce what you've been doing, but that's the point where actually I want to move. Like, can we find a connection? I indeed think that in this measure theoretic framework, we can get there, namely the interval, the uncertainty models and forecasts that we're considering, or in a way less general than what you're considering, namely effectively compact classes of precise forecasting systems, measures. But well, we start from, we originated from a martingale theoretic framework, and then we proved this equivalence. So, well, I think it will be interesting to see what's more to it, or well, what ideas of ours and yours could be fruitful for the both of us. Yeah. So one question I actually wanted to ask, because I didn't have like a lot of time to read the paper, the one that I showed in the beginning. One of the questions I had actually is what I noticed when you introduce the notion of randomness with respect to class of measures, is that, well, I didn't notice, I just read it, it's in terms of deficiency functions.
Yeah.
So one question I had is, okay, I'm now moved to this measure theoretic notion. Does your notion of Martin-Löf randomness that you've defined in terms of the efficiency functions, is there an equivalent definition in terms of tests, as I hear?
Yeah. Tests. What you say by tests is called in the paper probability bounded tests.
Okay. Yeah.
And also there are expectation bounded tests, which are technically more convenient, but they differ from the probability bounded only by some logarithmic term. So if one of them is infinite, the other is also infinite. For randomness, it doesn't matter at all.
Okay. Yeah.
So I think that kind of, no, actually, it's bad to have too many definitions. So to have a definition, you need some reason, some theorem that explains why it's a correct one. And for this computably closed class, I think the theorem that they proved is that as something is random with respect to the class, if there is a measure in the class, with respect to which it's uniformly random.
Yeah, and that's
this is kind of uniformly random, but it's also a natural thing. So there is kind of equivalence between two intuitive idea. So we have a class of measures, and when we our class of hypotheses, we know that our system behaves in this way with some parameters which we don't know. And then we want to say whether our observed behavior is compatible with this theory. And this is the general notion which we try to define. And it seems that you also have the same idea, but you just consider the hypothesis of the class that there is an interval and every independent interval at every place. So of course, I think that if you want to introduce a new notion of randomness, you should have some kind of explanation. Either it's equivalent to the old one, which is good, or it's not equivalent but has better properties, and then you should say what are these better properties and why they are better. So it's kind of so one should I should think more about what this definition gives and how you prove this equivalence result for. But for example, you can say that yes, it's equivalent, and moreover, we have now a martingale characterization for randomness with respect to some specific closed classes. And this will be one kind of what if you say what is that in one sentence, what is the achievement, that you have the martingale characterization for randomness, or maybe some better properties in some other sense. And what Wolfgang Schäfer tried to do, it seems, is to do it almost to make a sliced, to do not never consider anything which is in the entire space, but consider only things which happen along a path. So somehow the idea is that if you have a sequence and you have a prediction for a next zero, probability of the next zero, and then you have the real experiment, you should be able to say whether the experiment is consistent with the assumption, not looking into what the prediction says for other sequences which are not observed. Somehow what is should be important is only things that happen around the actual path. But in this way, somehow what you're doing is somehow in between. You consider still consider the martingales everywhere and predictions everywhere, but you split the gain by steps. So it seems like you are in my first impression, maybe false, is that you somehow do go halfway. You stop in the middle of some transition, which is a bit strange for me. But maybe it's a completely wrong impression. But it's just what I feel when I look at your definition.
Okay, well, I didn't have the feeling that you make certain cuts. You just said forecasting system, just a betting strategy that you define beforehand, or well, the super martingale, and then just the game runs.
Okay, just imagine that you and your girlfriend are just playing on one specific day, and you have sequence, and you have predicted something, and she made some bets, and something happens on this way. And it seems that you should be able to say who is the winner somehow, whether the sequence looks random according to your predictions good or not, without asking you what you will predict if you would have seen something else, or asking her what she would bet if the sequence would be something else. Somehow to avoid this. I believe this was the initial idea of Wolfgang Schäfer. You don't need to consider entire space. You need to consider some things that happen around your path. But okay, but indeed we have to finish maybe. So I just want to thank you on behalf of all the participants. And if there are any questions or comments.
I have a purely technical question. Just in the middle of the talk, I was distracted by the water dropping from the ceiling. So I have a question. Are you going to publish somewhere the recording of this talk?
Yes, sure. We have a channel.
Right?
Yeah. And then you can add the sound of the water artificially to make it more realistic. Yeah. Okay, so maybe we should look more at what you wrote, and maybe you can also send the list of references for the published things and some kind of guide what we should read, what we should avoid reading, and so on.
You can read you can read everything.
Yeah, but you can eat all the mushrooms you see, but some of them will kill you. Okay.
And
that's feast.
But it's your problem.
Related
not
question. Question. Do you have some link to your slides? We will put it all also on the web, on the site of our seminar.
Well, I can send you. Well, you're not that professional, but if you like them, well, I can definitely send them.
Okay.
And maybe I will check them once again for.
No, they are very professional. You imitate handwriting perfectly.
This is an imitation. Oh,
yeah.
Well, okay. Well, for me also, well, thanks a lot. Well, for wanting to listen. I hope, well, you learned a few things. Well, also thank you for drilling me. Yeah, I found it very interesting. Thanks a lot for the the bunch of questions. It was very nice actually to try to explain something in that way.
By the way, do you know that your imprecise system is exactly as happens in the bookmaker agencies?
What do you mean by bookmaker agency?
No, you can bet on sport events. For example, there are two outcomes.
There are buying price and selling price. That's
no, they publish two coefficients, and they correspond to imprecise. So, actually, the sum of inverse coefficients is always a little bit larger than 1, and the coefficient is how much you win making a certain bet. And if the sum of the inverse coefficients is exactly 1, that corresponds to precise forecasting. If it is larger than 1, that corresponds to imprecise forecasting, and exactly you have the same models. So that's good for advertising of your
it's good for advertising, but still that's what Wolf and Schaefer say, that you never know what the betting agency would say about the coefficients for this game if the yesterday's game had a different result.
Sure, I agree completely with you about that minor point of their definition, right? But I would stress that there is also a good point, and the good point that their approach corresponds to real bookmaker agencies.
Yeah, along one path. Yeah.
Along one path. Yeah, exactly.
Yeah. But no, the idea of prediction of prediction interval probability is, of course, you know, this interval.
Because in reality there is no probability actually. For example, nobody knows who will win tomorrow, and there is even no probability of that. And somehow the bookmaker agencies find those probabilities somehow, but in an imprecise way, and that corresponds to coefficients they make.
No, they're just not. They find it very easily. It's buying price and selling price. It's like a market. So if people come and they shift the market,
how do you know who will come? They first they announce the coefficients, and then people look at the coefficients and decide whether they want to make a bet.
I think they change the coefficients when people make.
Of course, they can change it, but at the very beginning, they have no information at all. There are no bets made, but still they somehow announce some coefficients.
No. Originally, you are ready to change 1 ruble for $1,000 and $1 for 1,000 rubles to sell. But then, when people come and you accumulate some money, then they
you do not accumulate some money yet, because you accumulate money only after the event happens.
No, of course, but you have some reserves. You know what will happen with this prediction and with this outcome and this outcome, and how much you will win. And the initial bets are making you positive, and then you can close the interval to make. No, you can ask Vuyen, young, middle Vuyen, how they work as my theory, but just I think that this betting companies are adapting the predictions according to the amount of bets they have. And they just make it closer and closer, but I don't know. Okay, any other comments and statements or whatever you want?
Что у нас в следующий раз будет?
What we'll have next time? Not clear.
Not clear. Okay.
Okay, but
might I ask a question to you guys? One of the reasons we've started doing this is to do some kind of imprecise statistics, where the people usually have this preconceived idea that you should be able to describe uncertainty with a single probability, and you have some data, and then you do some stuff and you arrive at the probability for whatever is going to be the next thing, or that models kind of the data generating process. People kind of tend to capture the data generating process that they don't really know much about by a single probability that they try and kind of distill from the data. And so we don't really believe that's always possible. We don't see where that comes from, that should always be possible to do so with a single probability. And so it's from this idea too that we started looking at imprecise randomness, because if you can associate an interval with a sequence in some kind of like formal way through this randomness, then this kind of gives you a kind of non-subjective way of associating an interval with okay, an idealized infinite, fair enough, data sequence. So I think like if you come from this side, then the whole thing that you need to provide the forecasting system all at once in the beginning. Okay, if it's a constant forecasting system, this distinguishment disappears a bit, because okay, if you have to be constant, you cannot be changing based on what you've seen anyway, right? So then these kind of, we have some kind of data generating process that we imagine, and we want to kind of capture that process, describe it, that's kind of the statistical point of aspect of it, by one model. And then let's keep it simple and do one interval. But I don't know whether
you want the interval to be the same for all terms, or what?
All terms?
So you mean for no, you have a sequence of zeros and ones, and you assume that every step the probability is in the same interval, or what?
Exactly.
So for
imagine
example,
we have the,
if you see 0 1 0 1 0 1 0 1, then you are not trying to provide this interval somehow. No, imagine that the zeros and ones alternate, and you see the system. What you will provide as a theory for the systems?
You mean in that case, you would better have a non-stationary precise thing, because
I just want to understand. So you are looking for one interval.
Yes, but okay, fair enough. In some cases, I'm going with the assumption that we want a stationary description. But fair enough.
Okay.
As they do in the precise case. I mean, most statistical methods try and come up with one probability based on the data. They don't try and find the pattern. So under this assumption, we kind of wanted to know, okay, as a first step, if you have the complete infinite sequence, which of course never happens, but if you have that, what would then be the ideal interval to kind of associate with that sequence, to describe it by? And somehow we think that using one probability isn't always going to be possible. And so this kind of inspired this line of thing. I don't know whether, have you guys kind of got a statistical perspective on trying to do imprecise random? Is this something you
statistical perspective is when you have a sequence, you try to guess a measure, and you have a point, and you want to find a simple measure which explains well this point.
Yes.
What Kolmogorov suggested to do in this his structure function or alpha beta stochasticity. There are different notions of that, and there is some kind of abstract theory which shows that there are some sequences which cannot be explained easily in this way, and there are other sequences which can be explained, which are stochastic and non-stochastic sequences. This is something in this direction is known. So if you have if the question is what exactly is of course this is as always, this cannot be done effectively, so there are always all kind of obstacles to consider them as something practical, but some kind of theory exists for that. That's what I say.
And this is called stochastic sequences.
This is called algorithmic statistics, and it's called, Kolmogorov called it alpha beta stochastic sequences. And no, the main expert here in the audience is Vereshchagin, and there is even a survey on that written by him and me. What is known about this algorithmic statistics, but it's also again a long thing. So if you have some specific question, maybe you can just ask directly whether something is known or not known or whatever.
I was wondering, is there anything of that kind of field venturing into the imprecise case? Have you ever tried to do algorithmic statistics with your more general
class of measures?
Because for some sequences, basically, you cannot associate a measure with because they're not stochastic, or I don't know what the term was. So our idea is, okay, if you cannot come up with one model, okay, in theory, but let's like put all the practicalities aside for starters. If you cannot come up with one measure, then maybe you can try and capture the uncertainty in that sequence by an imprecise model instead. That does, okay, at the price of some conservatism, but does manage to capture and provide kind of like information about that sequence. And then you want to do that with a set that is as small as possible, basically. To have,
so the question
have as much info as possible.
The translation of this question into algorithmic statistic language is that normally we consider looked for x for a measure which makes the deficiency small. And now imagine that you are looking for a class of measures which make the deficiency small and is somehow precise, more as precise as possible.
Yes.
Does it make sense? So I don't know what Kolya or Lyosha, could you say something about this possible setting?
No idea, actually.
So you
didn't think about that.
No, if there is a class of measure, you still can consider randomness deficiency by randomness test with respect to this class of measure. So it doesn't look impossible. So it doesn't look contradictory. In this framework, it still can be somehow expressed, this setting. But I don't know whether there are any results of this type, and I think no. So maybe it's interesting to look at this. This algorithmic statistic is for finite sequences, and it makes it easier or more complicated. It's difficult to say, but it's a difference, a bit more finitistic setting, but still you can think. So of course you can consider a class of all measures, and then everything will be very random.
Yes,
but,
exactly.
But whether can you, looking at that sequence, you can make smaller the class,
this is
still keeping the...
Floris was talking about the smallest interval. That's kind of how we are thinking about that. Like, if what's the smallest interval that you kind of can associate with the sequence? We like to think of this in a kind of statistical sense. We see this interval as a set of measures, basically, depending on how you want to look at it. And so this whole question of, is there a smallest interval and all this kind of thing relates to this. Like, is there kind of a unique, best, most informative kind of set of models that we can put forward if we're learning from this particular sequence? Because there's all this kind of talk, well, we do imprecise probabilities, and there's a debate, and is this purely subjective imprecise probabilities? Is it just kind of, no, everything is probabilities, but you just don't know it? Or is there kind of something more, less subjective, but something objective, like some things just cannot be described by, some purely data stuff cannot be described by one measure, and you should use something imprecise if you want to capture it. Like, these kind of questions really touch at the heart of kind of what's the meaning of imprecise probabilities, and for that reason we kind of very much like them.
But let's look in the other way. So imagine you get a sequence with zeros, some zeros and ones.
Yes.
And you want to, and your conjecture is that there is some one stationary probability you're looking for. So you consider only stationary models.
We can generalize this, but yes, like focus on that context.
Then what is bad in the following trivial approach? Look at this sequence of zeros and one. Look at its complexity. If this complexity is close to the just the entropy, so to the logarithm of number of all strings with the same number of zeros and number of ones, then you say that this sequence has no other laws except for the frequency of ones, and here is the frequency of ones. It's what corresponds to Bernoulli's sequences. And if you see that this sequence have much smaller complexity, then it can be said just looking on the number of zeros and ones. then it means that it's not stationary. There are something which happens which makes it the stationary models not acceptable for explanation of such a sequence. So if you were just ask a philosophical questions, why you don't like this kind of philosophical answer? Why you need something else? That's.
Well, for one, if it's non-stationary but extremely complex, okay, then in theory you can try and describe it with that, and it exists. But in practice, try and do statistics that way. I mean, basically every statistical model that starts from a data sequence comes up with one probability. So the assumption basically seems to be all around in traditional statistics. So this, I see how
if you have a model which counts with some probability, I think that this there is nothing better than take a if you want to get some number, then there is nothing better just to take a frequency. It's strange that you have some explanation which is different from the frequency.
If you use one number, then yes, I will also use that
and
one.
Then
but the question is, when does it make sense to capture it by that one number, and when should we actually go for something more imprecise?
Yeah, the answer is that if this one number, if you just count the frequency, take the complexity of the sequence and compare it with the entropy, if complexity is much smaller than the entropy, then one number is not enough. If it's close to the entropy, this number is enough. Why don't you like this answer?
Okay, but if it's not enough, so I agree that in those, that's the cases where it's not enough. But then the question, your answer to what should you do then seems to be, then you should be using a non-stationary precise thing. And then there's two aspects to this. Like, so one, people don't do that. People want one object that's easy to describe. And an interval does that. And then there's also this other aspect that those are all these results we've been discussing. It might be that the only thing that describes the sequence, and I mean infinite sequence then, is a non-computable non-stationary thing. And then what does that mean? So these results that there might not be any computable precise thing that captures it. And so then, I mean, there's even moving to non-stationarity doesn't solve it, or you should give up on computability. But if we're doing statistics, I really cannot give up on computability.
No. So practical question. You know that if the sequence is not stationary, so it has complexity less than the frequency. But then maybe you can say that it's somehow stationary, not somehow still have some interval of frequencies, but it's kind of strange what you're trying to capture here. But okay, I should think.
I think with alpha beta stochasticity that there is not much to say. So either some technique helps to compress something and then it has some interpretation in alpha beta stochasticity, or it doesn't. But you need different reasons, I think. You cannot use reasons from Kolmogorov complexity of algorithmic randomness for finite sequences with imprecise probability. Okay, I missed some part of the discussion.
So we have some sequence which is just seems to be not stationary, but we want to say that in which case the imprecise stationary measure prediction is still acceptable. This something like this, but okay, but we need to think more about this.
No, but the first part of the biggest part of the talk was about a hypothesis. We want to test a hypothesis, and if we're lucky, our hypothesis specifies a unique probability measure. But then what happens if it specifies a class, and then they define the class using gamblings, these predictors with intervals and so on, and this makes sense. You're checking a hypothesis whether a certain prediction strategy is helpful. And so it's in the field of Martin-Liv randomness. But for alpha-beta stochasticity, where you want to fit a model, the general theory cannot provide a justification. Maybe a justification exists, but I mean, this justification by fitting a minimal sufficient statistic. I don't think it can make a connection. But it is possible that it makes a connection, but then it's for completely different reasons. Maybe there is some algorithm that works very fast using imprecise probabilities and is useful, and then you can say something with whatever theory, but just with computable things and Kolmogorov complexity, it seems very unlikely.
Yeah, okay.
Yeah, we never think about it in terms of complexity, really, because it seems to be, in the precise case, this is equivalent. In the precise 1/2 case, this is all equivalent, but beyond that, we seem to be talking about totally different things when we look at complexity versus the martingale or
Kolmogorov complexity.
Yes, exactly.
But in data science, you deal with finite strings, and you want to fit a model to a finite string.
No, look, yes, of course, if I eventually want to do real statistics, it needs to be finite. But the way we're thinking about it is, as a first step, let's try and associate an interval with an infinite sequence, and then try and come up. So that's kind of the first question we kind of asked ourselves: what to associate with an infinite sequence, and then as a second phase, we'd like to kind of think of, okay, what's kind of a statistical method that would converge to this best interval with some guarantees on this happening almost surely or whatever, like an estimator basically that then tries it. So we tend to split it in this way, like first try and associate some good interval with one sequence, just like in the precise case you would just consider the limiting frequency if it exists, and then second phase, try and come up with a statistical estimator that gives you this this limit frequency as often as possible, or with high probability, or whatever. And so we would like to do something similar in the imprecise case, where okay, for some sequences, 0.1, you cannot, infinite sequence 0.1, you cannot associate a single number with. You might be able to associate sometimes a computable non-stationary one, or sometimes that's not even possible, and you need to
probably Sasha already said it. I don't know what it means. Like, if you cannot predict anything, you use probability 1/2. If you say we restrict to computable measures, we cannot predict anything, and then you're interested in model regularity. Why not use probability 1/2 if eventually you will use some notion like Martin-Liv randomness, which is equivalent to compression, and then you can think about compression.
Okay, no,
now you lost me.
Okay.
Okay. No, I also didn't get what you're saying.
So then I'm saying nonsense. I will shut up now. Okay.
And also your microphone, I think, is just 90 degree rotated according to the right position. No? No, it's not the problem which prevents me from understanding you. It's my problem. No, but just for information, I can tell you this. Yeah. Okay, so thanks again. And
yeah, it's nice to hear from you, and very happy that I finally learned what you're doing.
Yeah.
So,
I'm happy that the message came over, Bruno. Yeah. I'm happy that I was able to answer what you put in your email. Super nice.
Yeah. Okay. So maybe in December or January, I will send you an email.
Would be very nice, really. Looking forward.
Okay.
To
Thanks.
yeah.
Or you can come both to Montpellier. Okay.
Yeah.
Thanks a lot. We will send a message about the next seminar. Yeah.
Bye.
Okay.
Bye.
Thanks a lot.
Ciao.